Hello colleagues, my name is Phoenix and this is the fourth episode of my SKSE modding tutorial series. In this video I will tell you a little about the calling convention that is used in the game. Next we will get the signatures of some function that is illustrate various cases. Knowing the signature of a function is useful for RE. Suppose you reverse some function. Knowing the signature, you can find out the types of arguments and their number. If this function has internal calls, you also know their return type. This knowledge will help you understand the logic of a program around this function. You will get information about the function itself as well as about its calls. Ida shows wrong pseudocode with wrong signature. Look. If you want to hook a function call or do an high-biac hook to add or change its arguments, for example, you need to know its exact signature. You also need to know the function signature if you want to call it from your plugin or export it to Papyrus. We'll talk more about hooks in the next video. So, calling convention. You can read in detail here. If you want to be good at reverse engineering and writing functional plugins, you need to know the calling convention. Today we will only talk about function signatures. In the next video I will cover the rest of what is needed for RE and hooks. As you may know, integer values are mostly stored and processed in general-purpose registers. You can see them here. There are also truncated versions for accessing parts of the registers. So, the low byte of RAX is AL, the next one is AR, both together is AX, the lower 4 bytes of RAX are EAX. First reading for CL, for example, is actually reading from RCX. For simplicity, we will not distinguish what size the data is stored and will simply say reading from rex, writing to rex, even if only part of the register is used. As you can see, IDA highlights all instances of the rex register. There are also floating point number. They are handled in the XMM0, XMM15 registers. So, convention. The return value and the first 4 arguments are passed in the registers. The remaining parameters are pushed onto the stack. The return value is in the rex or XMM0 for float. The first 4 arguments are in RCX or XMM0 for float, RDX or XMM1 for float, R8 or XMM2 for float, R9 or XMM3 for float. Thus, the caller must initialize the necessary registers corresponding to the arguments of the callee, and then call it. The result is in rex register or XMM0 for float. If the function has fewer arguments, then the corresponding registers are not used. If the function has no return value, then rugs is not used. Since we are doing RE, we are solving the inverse problem. We need to get the signature from the assembly code. When getting a signature, you first find out whether the given parameter is an integer or a floating point number, because the register in which the argument is passed depends only on this. Thus, int, bool, char, unsigned int, and void pointer are passed in the same general-purpose registers, while float and double are passed in XMM registers. The second step is to figure out the exact type of the argument. Further analysis of the function helps you with this. Let's focus first on determining the register in which arguments are passed. Consider examples from the documentation. In the first case, all arguments are integers, so they are passed in general-purpose registers. The 5th and 6th arguments are passed on the stack. In the second case, all arguments are floating point numbers, so they are passed through XMM registers. The 5th and 6th arguments are passed on the stack. In this case, the first argument is an integer, so RCX is used for it. The second argument is a float, so XMM1 is used for it. The third argument is again an integer, so stored in R8. The next argument is in the XMM3 register. The fifth and sixth arguments are passed on the stack. The same thing happens when getting the return value of a function. You need to look at whether an integer is returned or not. In the first example, it is an integer, so args is used. Let's assume that double is returned in the second example and not what is written now. In this case, XMM0 is used, as is the case with M188 actually. We can find out the exact type of an argument or return value by analyzing how register is handled in the function. Now I will show you some examples of getting a function signature. I'll leave a list of function addresses for latest SSE in the description. Let's look at the first example. ida shows an empty function, but there are instructions in the assembly. The first one reads a value from XMM0 and subtracts some game setting from it. Perhaps your work with game settings looks a little different, since I tested my script on this new database to conveniently display game settings. However, the meaning remains the same. Function reads the uninitialized XMM0 register. This means that the first argument of a function float or double. args register is still uninitialized while XMM0 is initialized. This means that the function does not return anything or return a floating point number. Float or double. You need to look at the instruction that work with registers. For float they end in SS, single. For double they end in SD, double. You can try both options in ida. With void, the function is still empty. This is natural since the function only performs calculations, does not call any other functions, but the result of the calculation was ignored. Therefore, the ida considers that the function does nothing. So, function returns a float. Here we have the function signature. Open the second function. Read from XMM and from RDX. As you can see, there are no more reads from other initialized registers. Before exiting the function, the XMM0 register is written to. Therefore, the first argument is a floating point number, the second is an integer, and the result is a floating point number. SS hints that the function handles floats. Sets the signature. You see C-style cast on the second argument. Take a close look at the assembly. It only reads from the DL part of the register. So the second argument is either bool or char. Let's stop on the achieved success and write char. If you want to find out the exact type, then you need to look at the caller functions and how they initialize the argument, as well as the possible value of this register at runtime. However, char or unsigned char is usually enough for all our future actions. Move on to the next function. Read from RDX. Write to XMM0 before exiting the function. So the return value is a float, remember SS, and the second argument is an integer. Neither XMM0 nor R6 are read, that is, the first argument is ignored by the function. Look at the callers, Ctrl-X, of the function. Initialized R6 before the call. So the first argument is an integer. Set the signature. See how the function has changed. Now it is clear that R14 is a testObjectRefer pointer with name target, and before the call, the game adds hex B0 to it. This means that target at this point contains an actor pointer, and static cast occurs here. Open the definition of the actor structure. At offset hex B0 is the actor value owner structure. That is, the first argument to our function is actor value owner pointer. Let's find out the exact type of the second argument. Look at these two instructions. It's static cast to type float. Instead of explaining what this code means, I'll show you a website that helps a lot with RE, Godbolt. It compiles your code and shows the generated assembly instructions. Select the MSVC compiler. I don't know which version of Skyrim was compiled with, so I used the oldest one. Autuk optimization. I will now write 4 functions for converting integers to floating point numbers, and you will find the one we need. Here it is. Thus, there was a conversion from int to float. Fix the signature. As a conclusion of the subject of the exact register type, look at the following function. First, fix the SC style cast. Open the function code in a new window. I'll call v6 uns. This is the first byte of the RSI register. Zeroed here, checked for 0 here, and most importantly set to 1 if the 0 flag is set. This means that SIL contains either 0 or 1. This means that the function returns a bool. Correct the signature. The cast has left. Look at the function. Move SX means there is a static cast from char to in32. You can check it in Godbolt. So the return value of the function is char. Verify this by opening the function. As you can see, the BPL register is set to -2. That is, it's signed char. Fix the signature. The function itself returns int32. Fix the signature. The following function has a user call. This means that either does not know what argument the function has, so each argument has a register associated with it in which it is passed to the function. See, both R6 and XMM0 are now in use. Usually this situation occurs because of the XMM0 register. In this case, the argument is not used in the function, so you can simply remove the current signature and either set the new signature itself. Now you can see the correct registers and return value. To know the exact types, we need to analyze the function further, as we did before. As the name suggests, the first argument is magic caster. Set it. There will be a case where a function has a user call, but removing the signature and asking the IDA to get it don't work. Move on to the next function. The signature is no longer user call, but an initialized variable has appeared. The internal function signature is also user call, requiring the XMM0 register. In another case, IDA may not remove user call even from the current function, and your signature does not change after its removal. It's possible that older versions of IDA did not change the Usercall signature if initialized variables would appear after that. This is due to nested Usercall calls. You need to fix all internal functions, then IDA can find the signature. Jump to the inner function in a new window with tab, double-click F5. Usercall signature. Delete the signature. Again, an initialized variable. There is a comparison with the 0 of the XMM0 register. Of course, this is the return value of the function before. Open it in a new window. IDA often writes int32 as a default return type. Fix the signature. Return to the previous function. Press F5. The initialized variable is gone. The comparison happens right in the if. Return to the original function. The signatures has been correct. Unfortunately, it's not always possible to determine whether a function is void or not. Move on to the next example. Reading from RCX, write into memory by the second argument. IDA determined the types of the arguments correctly. Both arguments are pointers since memory is accessed using them. The second argument contains a pointer to the answer. I'll call it ans. That is, the function read unarmed damage and writes to ans. What is the return type? There is a control flow path where rex is not initialized, but XMM0 is always initialized. Therefore, the function either returns nothing or returns a float. Try both options. As you can see, the function looks fine in both cases. This is true. It's impossible to understand from this function what its purpose is. To calculate, write the result to ans, return void, or calculate, write the result, and return the same value. To figure out the return type, you need to look at the callers and see if they use XMM0 register after the call. In the first case, a static cast from float to int occurs before exiting. Confirm this with Godbolt. Same instructions. So XMM0 is not used. It's also not used in another function since further along the code there is a write in XMM0. That is, the function is most likely of type void. Again, there is no way to tell exactly what type a function is. If some caller uses the return value of a function, i.e. after the call reading from args or XMM0 occurs, then the function definitely has return value. If no caller uses the return value, then we can assume that the function is void. As a conclusion of the void or not topic, look at 3 functions that I will write in Godbolt. I will now write 3 functions that have the same assembly code, but differ in return types. Each function takes 2 pointer arguments and change the return value in them. The first function returns nothing, the second returns the computed int, the third returns the computed float. As you can see, completely identical instructions were generated, that is, the function match byte by byte. Thus, just by looking at the function, it's not always possible to know its return value. Look at callers. Now I will tell you how to work with local variables and pass the fifth and other arguments through the stack. You can read more here. Open the next function. Fix the signature. Note that it has 5 arguments and the callee has 6. As you can see, there is sub RSP instruction at the beginning and add RSP instruction at the end. So this function uses the stack to store local variables, call other functions, and pass fifth and subsequent arguments to calls. At the beginning of the function, RSP points to return address. This is used by read instruction. Next, hex 20 bytes on the stack are called shadow space. The function uses this memory as it sees fit. You might think that this is a possible place for first 4 arguments, because the fifth and subsequent arguments follow further down the stack. A function can use the stack for local variables by calling sub RSP and add RSP instructions. Thus, RSP value during the execution of the function body is less than at very beginning. Ida helps you see arguments passed on the stack. Look, A6 is the fifth argument. It has address plus hex 28 on the stack, as I said, since the fifth argument has address old RSP plus hex 28. Working with it looks convenient too. Accessing it looks like RSP plus stack offset plus variable name. The stack offset is the number by which RSP was decremented at the very beginning of the function. In our case, it's hex 38. RSP plus stack offset is the RSP value at the very beginning of the function, before sub RSP instruction. A6 is plus hex 28, meaning it's actually reading from memory at old RSP plus hex 28, as I said. To call a function, you need to provide shadow space. To call a function with 5 or more arguments, you need to provide shadow space and then put the fifth and subsequent arguments. Thus, hex 20 bytes from the current address at RSP will be shadow space. Starting from RSP plus hex 20 will be the fifth and following arguments. In this function, variable a5 has address minus hex 18, so RSP plus hex 38 minus hex 18 is accessed. That is, a float is placed at the address RSP plus hex 20. This is the fifth argument for Kali. var10 variable has address minus hex 10, which means that is the sixth bool or unsigned char argument was written to the address RSP plus hex 28. After call instruction, return address is pushed onto the stack and configuration already described by me will be obtained. I'll show you what it looks like at runtime. Launch the game, open cheat engine, move to the address of this function, set a breakpoint with F5. Get in the game and attack. Show full stack. Address at RSP contains return address. Next 4 lines are shadow space. Next is the fifth argument. It is char, so only 1 byte will be read here. After executing sub instruction, new lines appeared on the stack. Return address is now at RSP plus hex 38. Next, it reads from RSP plus hex 60, which means RSP plus hex 38 plus hex 28. That is, it reads from the fifth argument. Next, the register R8, the third argument, is set to 0, and RSP plus hex 28 and RSP plus hex 20 are initialized, the fifth and sixth argument for Kali. 4 lines before them will be shadow space for the Kali. Next, the third argument was initialized. Note that after the function call, values in shadow space have changed. Kali and its eternal calls used it for their own purposes. Next, the stack is cleared. Before executing read instruction, RSP again points to the return address. Now you know how to get function signatures. First of all, this is necessary for either to display the correct pseudocode, and secondly for hooks. Usually, either manages to get the signature. Otherwise, sometimes it's enough to just remove the signature and let it try again. Before doing this, you should make sure that there are no Usercalls calls inside the function. Either sometimes fails to detect the signature for function. Often this is due to float types. In this case, you have to find out the arguments yourself and manually correct the signature. To do this, you need to analyze which arguments are read from and which ones are written to. Also, in case of difficulties, you should refer to calls, since in that place you see how function arguments are initialized and how the result is used. You will need the skill to determine the signature of a function many more times, both with RE and with hooks. In the next video, I will tell you about hooks, and we will also try to find and write a hook that adds a new feature to the game. Play C++, reverse Skyrim. See you in the next video.